Welcome, this is Professor Ridge, and today's lesson 6.4, Graphs of Logarithmic Functions. Our first learning objective for today, identify the domain of a logarithmic function. Finding the domain of a logarithmic function. Recall that the exponential function is defined as y equals b to the x for any real number x and constant b greater than 0, provided b is not equal to 1, where the domain of y is all real numbers, negative infinity to infinity, and the range of y is the positive real numbers, so from 0 to infinity. So in the last section we learned that the logarithmic function y equals log base b of x is the inverse of the exponential function y equals b to the x. So if you remember about inverse functions, we're switching the x and y. The domain becomes the range becomes the domain. So the domain of y equals log base b of x is the range of y equals b to the x for the exponential function. So the range is 0 to infinity. So the range for the exponential function is the domain for the log function. Right, that's key. We're switching the x and y. And then, conversely, the range of y equals log base b of x is the domain of y equals b to the x. So that's all real numbers. Again, just look, we're switching the x and y. And then transformations of the parent function y equals log base b of x behave similarly to those of other functions. So we can do all the same transformations that we learned earlier with the shifts, stretches, compressions, and reflections. Okay, so let's look at example 1 here. Identify the domain of a logarithmic shift. So what is the domain of f of x equals log base 2 of the quantity x plus 3? So if the parent function is basically, again, what I call the base function or basic toolkit function, so we can add this to our list of functions we should know. Okay, so if our base function or parent function, as the book is calling it, referring to it, is log base 2 of x, we know from what we just talked about that the log function is going to be the range of the exponential function. So the domain will be from 0 to infinity, right? So 0 to infinity, but then we're shifting it. The plus 3 shifts it to the left 3 units. So you can just think about, all right, so if you're on the x-axis and the domain's from 0 to infinity, and then we're going to shift it left 3 units, it's going to start here. So that's one way to do it. Another way to do it is just the how-to up here. Set it up in inequality showing the argument, that's basically the input value, has to be greater than 0. So you just set up this inequality, x plus 3 has to be greater than 0. Okay, and then you solve it for x, so you subtract 3. So x is greater than negative 3. And then again, so basically it's going to start here at negative 3 and go to infinity. So in interval notation that'd be, and we're going to use a parenthesis because there's no equal to. Oops, not 0, negative 3 to infinity. So that's our domain. Okay. Okay, example 2, identify the domain of a logarithmic shift and a reflection. So what is the domain of f of x equals log of the quantity 5 minus 2x? So again, you can think about it through the transformations and think about how that affects the domain, or we can just simply attack it algebraically with this technique here. So again, we can think about the transformations if you want, or you could just say, okay, let's take the input value here, the input argument, I guess, 5 minus 2x. And we know that for the parent function, that has to be greater than 0. Okay, and then just solve this for x. So subtract 5. So this, again, we're working on the domain. We're not solving anything as far as the original equation. We're just identifying the domain. Okay, and then hopefully you don't forget that when you divide both sides by a negative number, you got to flip the inequality sign. So negative, negative make positive. And again, we're on the x-axis, so if I think of a number line, right, here's 5/2. We put an open circle, and I'm doing less than, so that's this way. So if I want to write it in interval notation, it's going to be a parenthesis. We're decreasing without bounds, so we're going to say we start at negative infinity. I mean, technically we're not starting, but that's the way I think of it. Start, stop, from left to right. Okay, so that's our domain. Okay, and on to the next learning objective, graph logarithmic functions. Okay, let's start out with the base graph of y equals log base 2 of x. Now, from what we learned in the last section, we know that this is the same thing as, if I do it exponential form, 2 to the y is equal to x. Okay, and we also learned that the inverse, we're going to switch the x and y. So let's do the inverse of this one. The inverse would be, so I'm going to switch the x and y, and I'm going to switch it around, so it'll be y equals 2 to the x. Okay, so this one, if we did x, y, and we put in 0, 2 to the 0 is 1. Put in 1, 2 to the first is 2. 2 squared is 4. 3, 2 cubed is 8. And then if I do negative 1, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8. And if we do the inverse of that, so we're going to switch all these x and y's. If we did log base 2 of 1, it's going to be 0. Log base 2 of 2, it's going to be 1. Log base 2, now the next one is, we're going to go to this one. Log base 2 of 4 is 2. And then the next one's going to be 8. Log base 2 of 8 is 3. Now the other way I could do it is I can just think of it in the exponential form and just think, okay, if I'm doing exponent, but the exponent now is y, so I'm going to put in my 0, 1, 2, 3 for y, and then negative 1, negative 2, negative 3, again for y, and then when I plug it in, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. And again, so there's two ways you can think of it. You can think of it as the exponential form, put in your 0, 1, 2, 3, or think of the inverse, which is y equals to the x, figure out that one, and then switch all the x and y's. So 0, 1, we switch it, 1, 0. And then this last one would be 1/8, 3. So whichever one works better for you. I just want to, again, emphasize, so let's make this log, well, first let's graph the exponential one. So 0, 1, 1, 2, 2, 4, 3, 8, negative 1, 1/2, 1/4, 1/8. Okay, so that's the exponential curve. Now let's do the log curve. So this one is y equals 2 to the x. Now let's do the log curve. So 1, 0. And recall that if we graph the inverse function, here I'll make this red, it's through the line y equals x. So basically the x and y are equal to each other. So -6, -6. See, I'm going through 0, 0, 1, 1, 2, 2, so on. Up to 8, 8 there. So that's the line y equals x. And if I do the mirror image, again, if this was on a piece of paper and I folded it on that dotted line, this would match up with the logarithm one. So if I do the logarithm one, it's 1, 0, 2, 1, 4, 2, 8, 3, then 1/2 -1, 1/4 -2, 1/8 -3, and then I have now on the exponential function we have a horizontal asymptote, and for the log function we're going to have a vertical asymptote, right? So it switches. Okay, so this is our y is log base 2 of x. So this is our base function or parent function, and then we could do all the transformations to that one. We can do log base 2 of x in parentheses x plus 3, so that'll move it left 3. Okay, we could do the stretches, the vertical shifts, we can move it up, down, horizontal shifts, so on. Okay, so some characteristics of graph of the parent function. So f of x equals log base b of x. So for any real number x and constant b greater than 0, where b is not equal to 1, we can see the following characteristics in the graph of f of x equals log base b of x. So it's a one-to-one function, so you can see it's going to pass both the vertical and the horizontal line tests. So the vertical line test would be the function part. And you can see every horizontal line hits it just once. So it's a one-to-one function. And the inverse would be the exponential function. Okay, so same thing if b is greater than 1 or b is between 0 and 1. So you get the same for both of those. The vertical asymptote x equals 0, so that's this dotted green line on the y-axis for both. The domain, so again, if I smash all the points on the graph onto the x-axis, it's going to be from 0 to infinity for both of them. The range, it goes from -infinity to +infinity for both. The x-intercept is, it doesn't matter what b is, the x-intercept will always be 1, 0. Right? You're always going to get that 1, 0 right there. No matter what b is. So for any b, you're going to have the x-intercept 1, 0. And we have this property of logarithms. Log base b of b is always 1. So you're always going to plot that point b1, no matter what b is. Okay? And let's see, y-intercept, there's none, unless we have a transformation, right? We're talking about the parent function right now. It's increasing if b is greater than 0, so this is increasing. So it's going up as we move from left to right. And it's decreasing if b is a number between 0 and 1. So you can see it's going down as we move left to right. So it's decreasing. Figure 4 shows how changing the base b in f of x equals log base b of x can affect the graphs. So observe the graphs compress vertically as the value of the bases increases. Okay, so by the way, this is ln of x, that's the natural log of x. It's base e, which is about 2.718. Okay, so notice how as the base gets larger, so this is base 2, this is the curve, this is base e, which is about 2.718. See, it's getting compressed, the curve's getting flatter as you go out, so it's increasing more slowly. And then this log, that's the common log. Hopefully you recall that's base 10. So here's 2, 2.7, and 10. And you can see that they're compressing. Now, between 0 and 1, the higher the base, the quicker it's going to get close. It's going to approach 0 quicker, right? And so this ln is in between the red one, and the blue one gets there the slowest out of those three. Okay, so let's example 3, graphing a logarithmic function in the form f of x equals log base b of x. So basically just a base, what I call my base graph. So this is log base 5. So there's a couple ways you can do it. Here, this is technique the book's suggesting. Draw and label a vertical asymptote, x equals 0. So as long as there's no transformations, it's just x, then you're going to have a vertical asymptote, x equals 0. So we'll put a vertical asymptote there on the y-axis. So that's x equals 0. That's a vertical asymptote. And then plot the intercept. 0, 1. Oh, sorry. That's for exponential. We're doing log. So it'll be 1, 0 for the x-intercept. Then you're going to do b, 0. So b, in this case, is 5. So we're going to do 5, not b0, it's b1. Because log base 5 of 5 is equal to 1. So if the base and this number match, it's just going to be equal to 1, because we're saying 5 to what power equals 5. 5 to what power equals 5? Well, obviously that's 1. Okay, so 5, 1. And then you're going to draw a smooth curve through the points. I like to do a -1, too. I like you to do 0, 1, -1. And then we're going to say this is 1/5. See, 5 to the -1 is 1/5. So the input value has to be 1/5. Log base 5 of 1/5 is -1. So I like to do that point as well, just to kind of, so 1/5 is here, to kind of give me a sense of how fast it's going over to the asymptote. Now, draw a smooth curve through the points and going towards the asymptote, right? So we're getting closer and closer to 0, and try to do this as smooth as you can and hit that point, and it flattens out. So this is y equals log base 5 at x. State the domain. So the domain is -infinity to, no, it's starting here, 0 to infinity. So 0 to infinity. And then the range. So again, it's going from, there's an arrowhead here. It's getting closer and closer and going, but it's decreasing without bound over there as x gets close to 0. So that will be, the range will be from -infinity to infinity, because this is, even though this is flat, it's actually going up just real slow. So it'll hit 2 at 25, hit 3 at 125, hit 4 at 625, so on. So it's going up, just going up real slow. And then the vertical asymptote, x equals 0, which we already did. Okay, so just, here they're just telling you to do 2. I like you to do 3 points. So And again, the way I do it is I actually just think, okay, so I want to do y equals log base 5 of x. I think of it in its exponential form, 5 to the y equals x. So I'm going to pick 0, 1, and -1 for the y. Plug it in. 5 to the 0 is 1. 5 to the 1 is 5. 5 to the -1 is 1/5. And I'm going to plot those 3 points. And then draw in my asymptote. And then draw in my curve. Okay? So that's the way I do it. Okay, graphing transformations of logarithmic functions. As we mentioned in the beginning of the section, transformation of logarithmic graphs behave similarly to those of other parent functions. So we can shift them, stretch them, compress them, reflect them, and the parent function y equals log base b of x without loss of shape, right? So we're going to have the classic log function shape. Just we can shift it, stretch it, compress it, or reflect it. Okay? So we'll start off with horizontal shifts. So it's just like any function. So it's acting on, the way I think of it is if it's acting on x, that's what does the horizontal things, right? So if I'm adding c units to the x before I do the function, which in this case is the log, that's what's going to shift it horizontally. And if you're acting on the x, it does the opposite. So if this is plus c, you're going to go minus c. If we did something like times 2, we'd actually divide by 2. Okay, so if you're acting on x inside the parenthesis before you do the function, it has the opposite effect. That's kind of the way I think through it. Okay, so we're going to take all our x coordinates and we're going to subtract c. So if c is, if this is plus c, we're going to move it to the left. If it's minus c, we're going to move it to the right. Okay, and then the horizontal asymptote gets shifted. I mean the vertical asymptote, sorry. And then the domain gets shifted. The range is going to stay the same. All right, let's look at example 4, graphing a horizontal shift of a parent function y equals log base b of x. Sketch the horizontal shift f of x equals log base 3 of x minus 2 alongside its parent function. All right, so if we have y equals log base 3 of x, remember the way I said I think of it is I think of 3 to the y equals x, and I'm going to put my 0, 1, -1. Now if it's a small base like 2 or 3, I go out to 2 usually. So I'm going to do 0, 1, 2, -1, -2. So when I plug in the y, so I'm doing it backwards because for me it's easier to think of it this way. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 3 to the -1 is 1/3. 3 to the -2 is 1/9. Okay, so I'm just plugging it into the exponential form, right? This is not the inverse because, see, I didn't switch the x and y. It's just 3 to the y equals x. So if I plot the parent function, 1, 0, 3, 1, I have a vertical asymptote. And then I'm going to do 9, 2. Oops. 9, 2. Again, that one you don't have to. I just like if it's if the base is 2 or 3, I usually go ahead and go out to 2. And then let's see, 1/3 -1, and then 1/9 -2. So we have a vertical asymptote. And then we're going to curve out to there. Make that a little smoother. Okay, so now watch this. That's the base one. Now this minus 2, we're going to shift it. So y equals log base 3 of x minus 2. This is going to be our base function shifted 2 units to the right. So a couple ways you can do this. You can say, all right, add 2 to all these x coordinates and then plot those, counting from the origin. Or what I do is I just say, okay, I'm going to graph this. I'm going to change it to this purplish color. So I'm shifting the origin 2 units to the right. Okay. And then I'm going to pretend this is the origin. I'm going to do the exact same points. So counting from here. So let me do this in purple. So I'm pretending this is 0. So this is 1. This one will be 2, 3, 4, 5, 6, 7, 8, 9. Okay. So then I'm going to plot counting from the pretend origin, which is right here. So I'm going to do 1, 0. Counting from here, 3, 1. Counting from here, 9, 2. And then negative, or 1/3 negative 1. 1/9 negative 2. And then I make my graph like that. Okay, so the black one is the parent function, and this purple one is the one we wanted to do, the shifted one. Okay, so for vertical shifts, we're going to have this this plus d out here, and that's going to shift it. Now, if it's so again, here's the input value, the x. It's inside the function. So if you think about how, if you were to did this on a calculator, you put the input value in, then hit the log button if it was base 10. And then it'll give you a number, and then you add d. So this is just straight acting on the y coordinate, right? Because this is log of x is in the parent function is the output value. And then you're going to add another number on top of that. So that's going to shift it up if d is positive, and if d is negative, it shifts it down. So if it shifts up and down, the vertical asymptote doesn't get changed, the domain doesn't get changed, and the range is not going to change, because if you add 5 or subtract 5, you're still going from negative infinity to infinity. So all those things are unaffected. Okay, so let's try this example 5, graphing a vertical shift of a parent function y equals log base b of x. So sketch the graph f of x equals log base 3 of x minus 2, and notice it's outside the parentheses. So that's acting on y, so that's going to move it up and down. Minus 2 would be down 2. Okay, and they want us to do the parent function. So the parent function is just basically the log base 3. So again, y, f of x is just y. So log base 3 of x. And then again, the way I do it is I like to think of it exponential form, 3 to the y. Remember, log equals exponent. Log equals exponent. So y is the exponent for the base 3 that gets you the number x. So again, I'm going to do 0, 0, 1. I'll go ahead and go out to 2. Negative 1, negative 2. Again, you can just do 0, 1, negative 1. But if it's a small base, I like to go out to 2. So if it's in small base, meaning just 2 and 3, right? 2 and 3, I'll go out. I'll do 2 and negative 2. But everything else, I'm going to do 0, 1, and negative 1. So 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. And again, if you're wondering what I'm doing, I'm just plugging it into the exponential form of the function. 3 to the 0, 3 to the 1, 3 to the 2, and just putting the answers for x, because see, we're plugging in y to get x. I'm going to plot my vertical asymptote. Oops. Let's make that red. Okay, and then I'm going to plot these points. 1, 0, and then 3, 1, 9, 2. Maybe I shouldn't go out that far because I'm not very good with this tablet that I'm using. And then 1 9 that. Okay, so this is my parent function. Not too bad, getting a little better. And then again, this is going down forever. It gets closer and closer. Okay, so now we're going to shift it 2 units down. So y equals log base 3 of x minus 2. We're going to shift the parent function. I don't normally call it parent function. I call it my base graph, but same thing. Down 2 units. So I'm going to basically take my x-axis and shift it down 2 units. Okay. And then my vertical asymptote remains here, so I'll make that one blue. Right next to the red one. And plot these points counting from the pretend origin. So if I want to do y equals log base 3 of x minus 2, I'm going to plot these points, count from the pretend origin. What I call the pretend origin is the shifting, right? So if the origin was at 0, 0, and we're going to shift it down to, this is my pretend origin. Okay. Again, that's my terminology, right? A lot of teachers they're like, what the heck are you talking about? Just this is the way I do it. Okay. Just a little word of warning there if you get help from someone else. So count from the pretend origin. Okay. So I'm going to do 1, 0, counting from here. 1, 0. So here, just to kind of emphasize this, this would be 1, 2, 3. So the x doesn't change because we just shifted it down, but the y changes. This would be 1, this would be 2, this would be 3, negative 1, negative 2, negative 3, negative 4, so on. Okay, so we're going to plot these points. I'll do this in blue or purple, whatever this is. 1, 0, 3, 1, 9, 2, 9, 2, 1/3, so counting from pretend origin, 1/3, negative 1, and then 1/9, negative 2. And again, we're doing that exact same shape. So this is the y equals log base 3 of x minus 2. Now, just a little word warning. If there's no parentheses, if I just wrote log base 3 of x minus 2, I'm assuming the one that it's the same as the one that I just wrote here. If I mean x minus 2 as a horizontal shift, I have to put parentheses around the whole thing like this. So if I don't write parentheses, I'm assuming the parentheses are around just the x. Okay? Unless it's multiplied. So if I had like log base 5 of 2x, right? That, whether I write parentheses or don't write the parentheses, that means the same thing. right? So 2x with or without the parentheses mean the same thing. Log base 3 of x minus 2. If I don't see parentheses, I'm assuming it's around just the x. So I'm going to do the x, take the log of whatever that number is, and then get that answer, and then subtract 2. Okay? So just be careful. So if you mean log base 3, here you're going to take x, subtract 2 first, and then do the logarithm. So these two things are not equal. These two things are not equal. Okay, vertical stretches and compressions of the parent function. So for any constant a greater than 1, the function f of x equals a times log base b of x stretches the parent function vertically by a factor of a if a is greater than 1, and then it compresses it if it's between 0 and 1. Okay? The vertical asymptote is not going to get affected. You're still going to have 1, 0 as your x-intercept, but your that b1 is going to get changed. Well, when we cover one, I'll show you what I mean. Domain, if we're just doing the a, the domain and range are unaffected. Okay, so the vertical asymptote, domain, and range all stay the same. You still have the same x-intercept, 1, 0. Okay, let's look at an example. All right, so example 6. Sketch a graph of f of x equals 2 times the log base 4 of x alongside its parent function. Include key points, asymptote of the graph, state the domain, range, and asymptote. All right, so the base graph is just the log base 4, or the parent function again. So y equals log base 4 of x. So again, the way I do it is I think of the exponential form. 4 to the y is equal to x. And I'm going to put in my 0, 1, negative 1. So 4 to the 0 is 1. 4 to the first power is 4. And then 4 squared is 16. See, it's already off my chart here, off of my graph. 4 to negative 1 is 1/4. So that's what I was saying earlier. Just do 0, 1, and negative 1. Unless it's 2 or 3, then I'll go ahead and do 2 and negative 2 on top of these 3. So this is the parent function, the base graph as I call it. At vertical asymptote, x equals 0. X equals 0. It's our vertical asymptote. And then we have, let's see, the domain's going to be negative, let's see, domain is negative infinity to infinity. Is that right? No, domain is, I'm thinking of exponential function again. So that's the range. Let me fix that. So domain's from 0 to infinity, and then the range is negative infinity to infinity. All right. So the parent function, 1, 0, 4, 1, and again it'd be 16, 2, so it's way out here before it hits 2. And then 1/4, negative 1. And then we have our logarithmic curve like that. Okay, so that is the base one. Now we're going to multiply this by 2. So if I want to do y, here, let me do something real quick. Oops. Let's move that sideways. Now, if I want to do y equals 2 times log base 4 of x. See, log base 4 of x is a y-coordinate, right? And then we're going to multiply it by 2 if you do order operations. So you're going to figure out what log base 4 is of x, and then multiply it by 2. Well, We already did that. So you just have to take this 2 value and multiply just the y coordinates by 2. So then I'm going to get 1, 0, 4, 2, 1/4, -2. And so what that does is it vertically, here we'll do this one in red, it's going to vertically stretch each of these points by a factor. So if you look at just the y value, it's 0. 0 times 2 is 0. The y value is 1. 1 times 2 is 2. If this is like, I don't know, 1.3, then it'll be 2.6 or something like that. Okay? This is at 0.5, it'd be at 1. This is at -1, so times it by 2, be at -2. So basically this is going to go down like that, and this one's going to come up something like that, roughly. Okay, so this is our graph y equals 2 log base 4 of x. Vertical asymptote doesn't change. Domain and range doesn't change. So all that's the same. Okay, example 7, combining a shift and a stretch. So sketch a graph of f of x equals 5 times the log of the quantity x plus 2. State the domain, range, and asymptote. So our base graph, or parent function, is y equals just log of x. Okay, if you don't see a base, that's base 10. So we're saying 10 to the y equals x. So I'm going to do, remember I'm putting in 0, 1, and -1 for the y. 0, 1, -1. 10 to the 0 is 1. 10 to the 1 is 10. And then this is 1/10. The plus 2 is going to shift it left 2. And then we're going to do a vertical stretch by a factor of 5. So I'm going to take these y coordinates and times them by 5. So that's going to get me 1, 0, 10, 5, 1/10, oops, 1/10, -5. Okay, so let me fix my graph here, because I got to go out to 10. I'm shifting it left 2 units. So now my vertical asymptote gets shifted. The red. I kind of messed it up, but okay, right there, close enough. Okay, so that's my, and then we have a vertical stretch, so that's the 0, 5, -5. So my pretend origin, so I'm going to graph from here, count from pretend origin. I guess I should learn how to spell that, huh? So right there. So again, counting from there, I'm going to do 1, 0, 10. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10. 5. 1, 2, 3, 4, 5. Counting from here, 1/10, -5. And then I'm going to make that logarithmic curve, right, as best as I can. That's not very good. It should be smooth. There shouldn't be that sharp elbow there. But anyway. hopefully you got the idea. So y equals log base 10 of x plus 2, then times 5. Let me try that again. So y equals 5 log. Reflections of the parent function y equals log base b of x. So the function f of x equals negative log base b of x reflects the parent function y equals log base b of x about the x-axis. So again, if you're thinking of the log base b of x is the y value and you times it by -1, it's going to flip it over the x-axis. So if you have a x and a y point, say right here, and you times the y coordinate by -1, it's going to flip it over and it'll be a reflection through the x-axis. Okay? So if you times by -1 out here, that flips it over the x-axis. The domain's going to stay the same, range is going to stay the same, and the vertical asymptote's going to be the same. Okay? They're all unchanged. Now if you put the negative inside the x, right, we're switching the x coordinate, so that's going to be, so if we have a point, and the xy, and you switch the x coordinate, that's going to flip it over the y-axis. Okay, so if it flips over the y-axis, the domain is going to now, so basically, if our original function was something like this, and when you flip it over the y-axis, it's going this way, your domain's going to be from -infinity to 0 now, and the range remains unchanged, and the vertical asymptote remains unchanged. Okay, but now the domain is going the other way because we flipped it over. Example 8, graphing a reflection of a logarithmic function. Sketch the graph f of x equals log of -x alongside its parent function. Include key points and asymptote of the graph. State domain range. Alright, so let me make I got to do both sides of this. And let's see here. We want to do log base 10. Ooh, they're not being very nice. I need to make this graph even bigger. Okay. So, or I can change my scale, but oh well. Alright, so log, here's the parent function. Y equals log base 10 of x. So again, I'm going to think 10 to the y. Remember, if you don't have a base, if you don't see it, the base is 10. So 10 to the y, that's our common log. 10 to the y equals x. I'm putting in 0, 1, and -1 for the y. 0, 1, -1. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the -1 is 1/10. So we get 1, 0, 10, 1, and then 1/10, -1. We have a vertical asymptote. There. We're going to graph our log function. That should be below the line there, but hopefully you got the idea. And then, okay, so now we're going to do the reflection, and remember the reflection is we're going to change the x values to -1. So basically we're going to multiply these by -1, just the x values. So and the y values stay the same. Oops. Log of -x. So basically it's going to be -1, 0, -10, 0. -10, 1, -1/10, -1. So let's do this one in purple. So we got -1, 0, -10, 1, 1/10, -1. Asymptote's going to stay the same, but it's coming from the other side this time. And then, I'm not used to doing this from this direction. Horrible. I'm just drinking Diet Coke, I promise. Okay, so this one's the reflection. Domain is, domain for this one would be -infinity to 0. The range would be all real numbers. And the vertical asymptote is the same. X equals 0. Example 9, approximating the solution of a logarithmic equation. So solve 4 times the natural log of x plus 1 equals -2 times the natural log of the quantity x minus 1 graphically. Round to the nearest thousandths. So this problem would be kind of hard to do algebraically, right? So if you have access to a graphing calculator, here's the techniques to do it with a graphing calculator. We're going to use Desmos. Again, I wouldn't ask you this question on the test unless I gave you the graph on the test, because you can't use a graphing calculator on the final exam. So but this is a good technique to know for if you ever come up to a problem that you want to solve this way graphically. So what the technique is, you're going to graph, you're going to call this one the left side, you're going to call that y1 equals 4 ln of x, and then the right side we'll call it y2 equals -2 ln x minus 1. And so okay, these aren't the graphs, so if you graph this one, let's say it does something like something like that. And then this one, let's say it does something like I don't know, because it's going to get flipped upside down. And then anyway, we'll figure it out later. So you're going to look for that intersection point, and whatever that x value, that's going to be the solution to this equation. So let's try it on Desmos. Okay, so again, we're just going to type in the left side. You don't have to write y equals, you can just type the left side in and it automatically takes y equals. I like to give them function names, so I'll call the left side f of x, and then just type in the equation, and then I'm going to do the right side, I'll call it g of x. You don't even have to put in anything, you can just write the left side, write the right side in 2 separate lines, and I'll graph them, because it just takes as default y equals if you don't type y equals. The only time that wouldn't be true if you typed in a number, right? Okay, so I'm going to type in the left side for f and the right side for g, and then see where they intersect. All right, so I typed in both of them. So the left side is this red graph, then the right side, and they intersect right there. And we wanted to go to how many places? 1.33853, we wanted 3 decimal places, and there's thousands. So x equals 1.3385, so that'll be 9. And that's our solution. Okay, so again, I type the left side in up here, right side in for G. I look for the intersection point, and the x coordinate is where both those y values are the same. So that's saying that the left side and the right side are equal to each other. They're both going to be 2.16629. Okay? And again, remember what I was saying earlier, I didn't have to type in that y equals or f of x equals. I can just type in just the left side and the right side. So it takes by default y equals, so I don't have to do that, but I like to do it because, you know, maybe I want to do something with those functions, something else later. So anyway. Okay, so we pretty much went over all the all the transformations. This should say transformations. So technically translations are the shifts, and then the other transformations we can have stretches, compressions, and reflections. So the general equation for all the transformations are y equals a, so that's the stretching or compressing, log base b, and then in parentheses x plus c. The plus c is the shifting left right, and the plus d is the shifting up down. And then if you have a negative inside with the x, that's the reflect about the y-axis. If you have a negative outside here, that's a reflect about the x-axis. So you can actually add those two into this one as well. So if x is a negative number, if it's negative x, not a negative number, if it's negative x, it flips it along the y-axis or about the y-axis. And if a is negative, that'll flip it about the x-axis. Okay, example 10, finding the vertical asymptote of a logarithmic graph. What is the vertical asymptote of f of x equals negative 2, x plus 3, what did I say? Negative 2 log base 3 of the quantity x plus 4, and then we got the plus 5. So remember, if we think about the parent function, it's just log base 3 of x. Right? And then that one we know that it's going to have a vertical asymptote at x equals 0. And then the plus 4 is going to move it to the left 4. So we got to move it to left 4. So now that's at x equals negative 4. And then the negative 2's, so basically the graph would look something like this. The negative 2 would flip it upside down, so it would go, so basically it would go this way now. And then the 2 would stretch it by a factor of 2, so it actually would be a little bit wider like that. And then the plus 5 would shift it up 5, right? So you kind of think of it order operations. So this is going to do shift it left. This does the negative, flips it upside down, the 2 stretches it, and then the plus 5 shifts it up 5. So all those transformations, the negative 2 and the plus 5, don't change the asymptote. So another way to do it is just kind of like the domain. Just look at this part and say that that has to equal 0. So this is the shortcut. You just say, okay, this thing in here has to equal 0. So x equals negative 4. So that would be your vertical asymptote. Okay? But if you wanted to go through all the transformations, you can kind of think of it that way too. All right, so it's just x equals 4. Negative 4, sorry. Example 11, find the equation from a graph. Find a possible equation for the common logarithmic function graph. So remember, the common function is common log is base 10. So So let's find some points on here. We got negative, let's see, that would be what? Negative 1, 1. We got 0, 0. We got 2, negative 1. And then, so we know it's base 10. So if we do y equals a times log base 10 x plus c plus d for our transformations, we're going to plug in, let's plug in the negative 1, 1 first. So negative 1, 1 is the y. Negative, by the way, if you notice that the asymptote here is right there, x equals 2, so we know c is going to be plus 2, because remember it's the opposite. So we're going to write this as, let me write that down, y equals a log of x plus 2. So now we just need to figure out a and d, so we just need to use 2 points. So let's use the negative 1, 1. So we put in the 1. So I'm going to do negative 1, 1. So remember that's xy. A log base of negative 1. Sorry. So negative 1 plus 2 is 1. And this is a basic property. Log of any base, log base whatever, of 1 is just 0. This is equal to 0. If you punch that in your calculator, you'll get 0. So d is 1. Okay, because 10 to the 0 is 1. Okay, so d is 1. So now we know that one. So now I got y equals a log of x plus 2 plus 1. And then let's plug in, 0 going to help us? 0, 0. No, let's plug in the 2, negative 1. So let's see, negative 1 equals a log base 10 of 2 plus 2 plus the 1. So that would be negative 1 equals a log of 4 plus 1. Subtract the 1 from both sides. So I got a log of 4 equals negative 2. And then divide both sides by log of 4. So those cancel, and you got a equals negative 2 over log of 4. And that's all our variables now. So our equation is going to be y equals negative 2 over log of 4. You can punch this in your calculator if you want to approximate. That's pretty bad. Let me write that again. Okay, so negative 2 log of 4. You don't need the parentheses, but the book tends to do that. So that's the a log base 10. So you don't have to write it. X plus 2, and then the plus 1 on the outside. So that's our final answer there. And let's see, if you put in 6, let's see if we get something close to negative 2, just to see if we're on the right track. Okay, and you can see I put it in there. I got 2. In fact, if I just leave that as x, you can look at the curve, and it looks pretty close, if not exactly like the one that we have there. Right? So pretty close. You can even check some, oops, I don't know what I did. Okay, you can actually even check some points, like just click on it. So we used 1, negative 1, 1, 0, 0. Well, I don't know if we didn't actually use 0, 0. And then we did 2, negative 1. Right, so we plugged in those points. And then you can see there's 6, 2. or somewhere close to it. There it was. 6, -2, sorry. Okay, so that brings us to the end of that section. So again, practice, practice, practice. Go to the end of the exercise section. At the end of the section, do the exercise set, all the odds, many of the evens as you can if you're up to it. All right, have a great day, and I'll see you next time.